Hello, thank you for coming to our program area room here. It is one of my favorites, and I'm not just biased. So my name is Rialda Spahic. I'm a PhD candidate at the Department of Engineering Cybernetics, and I'm also part of the new business and operational models. And I'm also very lucky to have all of my supervisors in this room as well as a support, so I feel more relaxed. So the title of my PhD is Remote Operations and Future Operating Models, and I'm focusing on ensuring the reliability of unmanned autonomous systems. So as we all may know that remote operations rely on safety support functions such as maintenance, inspection, and monitoring. And this typically involves work under very challenging conditions, so low visibility and potentially even dangerous environments. So many years ago, the industry has figured out that we have new technologies to use for this purpose, to remove humans from dangerous situations and to use the drones or the robots or however you wish to call them. I'll call them drones. So the underwater drones. But I said rely on, and I want you to take a very quick second due to time restriction to see what comes to your mind when I say rely. To me personally, I say rely is to trust someone to do something. I rely on someone I trust someone to do something for me. And luckily for me, the Oxford Dictionary has the same. Reliable is that can be trusted to do something well. So what are we trusting the drones to do for us? We trust them with a really, really important task, and that is to increase the safety of remote operations. And by that, we mean to free us from unacceptable risk. So how do drones do this? So far, they are looking for potentially hazardous events. They are looking actually for the sources of harms, which are the hazards, through various inputs, through camera and to various sensor inputs. However, so far we have seen how the remotely inspecting with the drone works. We have some operators in the control rooms that are using the drone as a media to look for some potentially hazardous occurrences. But to free the operators from these really huge tasks and to free some resources, we can use even more newer technologies with the autonomous drones, and especially with the resident subsea drones that have been tested in the last couple of years. And these drones rely heavily on themselves, on the artificial intelligence methods. But what do we gain from this transition? So with the remotely operated drones, we have humans there who are the main brains, and they are trustworthy, they are explainable and predictable, and these are all positive things. And why are they explainable? Well, because the human will come to a conclusion and we can ask why did they come to this certain conclusion, and that's why they are also predictable and trustworthy. But the downside of this is that the humans aren't that good at handling so many complex tasks at once. The data that is incoming is huge, and it's a very resource intensive to look at the streaming data, and it's of course very time consuming. So with the autonomous drones, they are a lot better at handling complex tasks. They are a lot more efficient, require less time, and they bring us this sweet data that is the new gold these days. However, they also come with the downsides, which are extremely big data that then requires using of the black box algorithms, because as you may know that this kind of big data requires also complex algorithms to look through it, because who is going to look through the data to label it? By default, we would need 66% of testing data and the remaining of training data. And to label this training data is a really huge task. So we convert to the unsupervised algorithms that are very black boxed and they are unpredictable. So these are some things that we need to balance out as we go from low to high levels of autonomy, as we depend less on the operators and more on the AI and the data. But I keep saying the data. Data is actually this, here data is the key, is the main communication tool. And to see data as the key challenge, we need to understand that there are 4 V's when it comes to the big data. We have volume, which is the scale of data. We have variety, which is all sorts of different formats of data. If you look at a drone, it not only has cameras, it has all sorts of different sensors. And those are all different formats of data that we need to consider. We have velocity. This is something I've mentioned. The analysis of streaming data, a lot of data is incoming, and we need to stream it and analyze it very quickly to be on top of the situation. And of course, the uncertainty of data. I said the low visibility, very difficult and challenging conditions. So veracity and the uncertainty of data is a real challenge here. So we asked the question, do autonomous and manual drones then differ when it comes to this sweet data collection, and how? So for this, we have done an experiment where we have tested two identical campaigns, autonomous and manually collected data, sensor data on the environment and water measurements. We have tested anomaly detection methods that are looking for some discrepancies in data trends to tell us if there is something unusual going on in the data, and the classification methods that work to classify different water conditions. And what we have realized that these two are equally reliable for data collection. That is not a problem, but what the actual problem was the data itself. There were so many underrepresented data classes on one typical water condition, and the AI methods that we had to use for this data have classified these as anomalies, and they were discarded as noise, which was a problem because the data here was unreliable, not the drone. And why is this important? Why are the anomalies important? Because sometimes if we are visually inspecting the pipeline, we can come to biological growth, but we can come to a rupture or corrosion, and how do we react to this, and what are the priorities here? And this is where we need to find a balance between false alarms or noise and the actually significant information, and to know when do we react to which one. And when does the drone actually trigger an alarm to operators and say, hey, we need to inspect this further, or ignore it as our experiment did. So this leads to the main focus of our project, is to extract valuable information, hazardous occurrences from massive amounts of imbalanced data. And for this, we are developing our very own so-called warning identification framework, because there is, fortunately for us, there are very little hazardous occurrences. But that means there a big scarcity of hazardous events in the data, leading to this data imbalance or the data biases. And additionally to that, the huge amounts of data means that there's a huge amounts of unstructured and unlabeled data that we don't know what we're actually looking into. And thirdly, there are two extreme shortcomings of anomaly and classification methods. Anomaly detection and classification methods is that they can either overwhelm with false alarms, or they ignore the potentially significant information. So we have figured out that since we are looking for hazards as the sources of harm, and something that also looks for hazards as sources of harm is risk analysis. And the risk analysis steps and anomaly detection steps are very much overlapping. So we can actually use these two disciplines and overlap them to use insights from risk analysis to semi-supervise or set decision boundaries for anomaly detection and classification to be more certain of what we are looking into. And how do we do this? Risk analysis is giving us the lists of hazards. For each hazards, we can see the likelihood, the frequency of their occurrence, the sequence of events that leads to them, and the consequence of that hazard. We input this as a decision boundary to anomaly detection to be more certain of the true anomaly detection points. So this is something that can be called semi-supervised anomaly detection. And how does this look in practice? So the risk analysis gives us the symptoms of what to look for during a visual examination of an underwater pipeline. So for example, for the external corrosion, we can look for material type, discoloration, thinning, and surface connected cracking of the material. And for other sensor measurements, we can look for typical temperature, pressure points, and dimensional measurements. And most importantly of all of that, the consequence analysis from risk analysis can let us know how the UAS, or the unmanned autonomous systems, can prioritize their response actions. So once we detect an anomaly, it is time to actually classify it to know what we are dealing with. So since we have the time series data and we are connecting the risk analysis insights and the anomaly detection methods, we propose our novel categorization of anomalies by their temporal change, which are the expanding anomalies that can tell us in time the rate of corrosion and ruptures, when to react to it, the reappearing and disappearing anomalies to tell us seasonally also when does something happen, such as biological growth or some biological occurrences, and the frequent or recurring anomalies that can differentiate normal from anomalous data. And why is the frequent or recurring anomaly important? Because in anomaly detection and classification methods, if there is a frequency of certain data, it means that it's normal. It naturally assumes that this data is then normal because it's constantly appearing. But what if something we don't like is constantly appearing and then the AI confuses it with normal? This is where this comes in handy, because then we can differentiate the normal from anomalous data, because risk analysis insights told us what is potentially anomalous or hazardous. And this leads me to the point that is very important. It is the early recognition and reaction to anomalous occurrences. Tracking anomalies in time allows us to early recognize how the anomaly is developing and when, if it's developing, and when is it a possibly hazardous, and if we should actually react to it or not. Through this project, we need to balance actually the social challenges and the technical challenges. We need to solve complex tasks and have early answers to upcoming situations, but we also need to have explainable results. We need to know why did the drone react in a way it did? Why did the AI method give us a certain result? We need to know how to explain the certain reaction that we are taking. And we need to prioritize the mitigation actions, because we are talking about the assets and the environmental challenges here. So we need to change the way data is communicated, and that is transparent, understandable, and efficient. With this way of looking at anomaly detection, we can focus on more important data from the huge collections of sensor measurements. We can have the prioritized responses from the underwater drones, and we can deduce the underlying causes of anomalous occurrences, because ensuring the reliability of unmanned autonomous systems and enhancing the safety of remote operations cannot be overemphasized. Thank you so much.